This is going to be a summary of different methods of graphing parabolas or quadratic functions. And I know this material is sometimes difficult for students to grasp quickly as we go through it just once in class. So you'll be able to use this video to fill in any gaps in your notes or to come back to later if you need some review. So on your worksheet, you can follow along and fill in your notes. Question 1 says, can we complete the square using just one side of the equation in order to find the vertex and axis of a symmetry and make a quick sketch? So we have an x squared parabola. Now something that'll give you a quick hint is because we have a negative value for a, we already know that this parabola is going to open down. And we know that that multiplier of 3 is going to make the y-coordinates grow faster, so near the vertex it will look narrower. But we don't know where that vertex is. So this first method, and then we'll use a shortcut later, this first method is to convert it to our graphing form. So we're going to keep f of x all by itself on the left side. And that's going to change our completing the square method a little bit. On the right-hand side, I'm going to factor the a value, negative 3, out of the first two terms. So we'll have a 3 in front of x squared, and then we'll have a 2x. And then this might seem odd to you, but this is where we're going to leave our blank for completing the square. And then don't forget we still have this negative 1 term here. If we had something like a 0 on the left-hand side, then I might move the 1 to the other side. But because it's an f of x, I want to keep this f of x isolated. So I'm going to only do things here working on the right side of the equation. So I'm going to fill in this blank to make this a PST, a perfect square trinomial. And you're going to see the trick here is if I add something to this equation, how can I keep it balanced? And the trick is whatever I add, I'm also going to subtract. So it's a little bit different than last semester where we worked on both sides of the equation. But to complete a PST, I still take half of this middle coefficient. So I'm going to take half of the 2 is 1, and I'm going to square it. So 1 squared is, of course, 1. And here's an important thing to watch. It looks like I just added 1, but don't forget the distributive property. I really added negative 3 times 1. So I just added a negative 3 to this equation. So how can I do no harm if I added a negative 3? Then I better take it away as well. So adding a negative 3, of course, is the same as subtracting 3. So if I put a plus 3 there, does that keep the equation exactly the way it used to be? So this is a cosmetic change. It changes the way it looks, but not its size. So now I can rewrite this PST as a glob squared, and I combine these two terms, and now we know about this parabola. So I'm going to slide to get some more space here for writing. So there's our graphing form. So we know that the vertex of our parabola is in the opposite direction for the x change. So remember that our vertex is at this value of h moves in the opposite direction. We would pick negative 1 for x. And our k value, the vertical transformation, moved in the same direction. So we change the opposite of this sign, but we do not do the opposite. Verticals are in the same direction, horizontal transformations in the opposite direction. Okay, now we're ready to graph this parabola. A quick sketch. We're not worried about making this perfect. There's our vertex, and we know that our a value is negative 3, so it's going to be narrow and upside down. And if you label your vertex, and we can see the narrower version. If we want more points, then we could label, and our intercept, our y-intercept might be an easy one. Let's go back to our original function. Do you see that if we put 0 in for x, we would get a y-intercept of negative 1? The two first terms would drop out. So we know that our y-intercept here, that might be another easy point to label. So there is the graph of number 1. All right, let's summarize then. When we completed the square, that process, can we come up with a way to avoid having to complete that square? And what we ended up with was the opposite of b over 2a as our x-coordinate. And you can verify that if you go back up and look at number 1. Our vertex ended up with -1 as our x-coordinate. And is that the opposite of 6 divided by 2 times -3? So there's our shortcut so we can avoid completing the square. So here's our quicker method. If you have a good memory, you can remember that our vertex is going to be at the opposite of b over 2a. So our vertex, I'm going to take the opposite of b, that would be a -4, divided by 2 times our a value would be +4. So the x-coordinate of our vertex will be -1. And then we find, and now I wrote over the top, let me erase that. To find our y-coordinate, we take f at that value. So now we know the x-coordinate of our vertex is -1. So to find the y-coordinate, I'm going to say what is f of -1. And if it was complicated, you could even use your calculator to do this. But I'm going to put -1 into our function. And we're going to come up with 2 minus 4 plus 5. So we will get a y-coordinate of our vertex of 3. So our vertex formula saves us from having to complete the square like we did in problem number 1. Okay, now that we know our vertex, look at what else we know here. A has a value of 2, so our parabola opens up, and it is twice as narrow. So I can do a quick sketch of the graph here. There's our vertex at -1, 3. Our graph opens up, and it's narrower because we're multiplying by +2. Our y-intercept is going to be at 5, so I could make my graph look a little bit more precise here. Whoops, I didn't do a very smooth parabola there, but I'm going to leave it. I think you guys can see our y-intercept is at 0, 5. I'm trying to write in a very small space here. All right, now let's see what we can do about x and y intercepts. Well, how many x-intercepts could a parabola have? Here are 6 different parabolas. It is possible for a parabola to have its vertex above the axis and open up, or have its vertex below the axis and open down. So it is possible for a parabola to have 0 x-intercepts. Or we have the possibility that the vertex could be on the axis and open up, or on the axis and open down. So it is possible for a parabola to have 1 x-intercept. Or our parabolas, of course, could pass through twice. Each of these parabolas has 2 intercepts. Is there a way to predict that? Well, remember that x-intercept is the same as the zeros of a function. We've been working with that. The zeros of a function are the values that make the y-coordinate equal to 0. So if we know how many zeros a function will have, then we know how many x-intercepts it will have. Well, if we can factor a quadratic equation, then that's one way to set it equal to 0 and factor it. But notice this first example doesn't have factors. So we would have to use quadratic formula. So if your question says how many x-intercepts, then you only need to look at the discriminant from quadratic formula. If you have to find the x-intercepts, then you would use the quadratic formula to find those values. So here our question says how many x-intercepts, so the discriminant from quadratic formula, remember it was the part that was under the square root. So if we get a negative value for the discriminant, then there would be only imaginary answers, so 0 intercepts. If that square root becomes 0, then there's only 1 double root. And if that discriminant is positive, then there will be 2 roots. So let's do each of those. So let's find the discriminant value here. So we'll take b squared, -1 is our value of b, and square it. And then minus 4 times our a value here is +1. Our c value is -1. So we can see that this discriminant is going to be 1 minus -4, so that's going to become 1 plus 4. So I wrote less than 0, and I mean greater than 0. So there will be 2 answers. So there will be 2 x-intercepts. And it looks like this underline should be a negative sign in our next problem. So let's find the value of the discriminant, or you could try factoring it first. But we don't need the answers for the x-intercepts, just how many there will be. So let's do our discriminant value again. B has a value of -1, so we're going to square it. B squared will be 1. Minus 4 times the value of A is -3. The value of C is -2. So here we'll have a 1 minus 24. So we can see that it's less than 0, so there will be no x-intercepts, none. And in our third example, we'll do again, b squared would be 64, minus 4 times a is 1, and c is 16. So here we have 64 minus 64 is 0. And when the discriminant disappears in quadratic formula, that tells us that there is only 1 double root. So that's when our parabola would be like this example, where the vertex would be on the x-axis. Let's put this all together then in number 6 and see everything that we know. When we look at this parabola in 6, the easiest thing to see is that a is greater than 0, so it opens up. It has a value of 1, so it is neither narrower nor wider. It's the same shape. An easy value to see here is that if x is 0, y is 5. So our y-intercept is always easy to see because we let x be equal to 0. We get 5. The x-intercepts are what we were just working on. The x-intercepts, we have to set the y side to 0. And we could use the discriminant to find out how many there are. But here we want to do more than that. We want to find out where they are. And notice that this one is factorable, so I don't need to use quadratic formula. I can see that the x-intercepts are at 1 and 5. Those are the 2 values that make the y-coordinate equal to 0. So those are our x-intercepts. And then we've got our vertex to find yet. We learned the formula for our vertex is -b over 2a, and then we can plug that in. So I'm going to do our vertex. The opposite of b is 6. 2 times a is 2. So our vertex has an x-coordinate of 3. And then to find the y-coordinate, we're going to put 3 into the function. And you could use your calculator if you don't want to do that arithmetic.